Hello everyone, I welcome you all to today's discussion session wherein we are going to discuss the CAT 23 paper, the slot 2 paper particularly, CAT 23 slot 2 paper, the QA section. So as you all know, we had 22 questions. Next, question number 5, let's look at it. The number of positive integers less than 50 having exactly 2 distinct factors other than 1 and itself is. So by the way, when you write any number n as a is a prime number, prime factorized form, a to the power alpha 1, b to the power alpha 2, c to the power alpha 3 and so on. So a, b, c are prime numbers, alpha 1, alpha 2, alpha 3 are say natural numbers. Then in that case, the number of factors, let's call it as f, will be given as whatever is a power here, alpha 1, we add 1 to it, alpha 2, we add 1 to it, alpha 3, we add 1 to it, and then we multiply. That is how we get the number of factors. That's the formula. So one thing that we can understand from this particular expression is, if there are 3 prime factors, a, b, c, there will be 3 brackets, alpha 1 plus 1, alpha 2 plus 1, alpha 3 plus 1. If there are only 2 prime factors a and b, then there will be only 2 brackets, alpha 1 plus 1, alpha 2 plus 1. And similarly, if there is only 1 prime factor, there should be only 1 bracket. So I am trying to draw some kind of correlation, some kind of relation between the number of prime factors and the number of brackets, the factors alpha 1 plus 1, alpha 2 plus 1, alpha 3 plus 1 that will have. Now here he says, number of positive integers less than 50 having exactly 2 distinct factors. Having exactly 2 distinct factors other than 1 in itself. So please understand, what does that effectively mean? That would mean number of factors of n, of the given number, suppose n, can I say should be equal to, we want 2 distinct factors besides 1 n itself, so overall it should be 4. So overall factors should be 4 and the number n should be less than 50 also. So how many numbers less than 50 have exactly 4 factors? Essentially that is the question. So how do we answer it? So how can we answer it? Let's try to look at it. So this left hand side number of factors expression is alpha 1 plus 1, alpha 2 plus 1 and so on, should be equal to 4. Now in how many ways can we have product of these brackets alpha 1 plus 1, alpha 2 plus 1, alpha 3 plus 1 etc. equal to 4, where we know alpha 1, alpha 2, alpha 3 are natural numbers. In how many ways can we write it? Simple. We could say there are only 2 ways of doing it. One is when you take alpha 1 as 3. So 3 plus 1 will be equal to 4 and alpha 2, alpha 3 all are zeros. They are non-existent. Or the second case, alpha 1 is 1, alpha 2 is also 1. That's the second case. And there is no other case besides this. Think about it. So there can only be 2 ways in which you can get 4 factors. One is if alpha 1 is equal to 3, so 3 plus 1 will give you 4. Second, if alpha 1, alpha 2 are both 1s, then 1 plus 1, 2 into 1 plus 1, 2, 2 into 2, 4. That's the only way, 2 ways in which you can get 4 factors. So that means we are looking for numbers of the type where the power is 3 or the numbers of the type where the powers are 1 and 1. So can I say, based on this, can I say the number n should be of the type a to the power 3. Alpha 1 is 3, only 1 prime factor. Or n should be a power 1 into b power 1 type of number, where a and b are prime numbers. Now when we start counting, a cube would mean perfect cube. So how many perfect cubes do we have less than 50? So we have 2 cube. It will have 4 factors. We also have 3 cube, 27. It will also have 4 factors. Now we can't go for next 5 cube and all, because a should be a prime. I can't say 4 cube. A should be 5. 5 cube is much more than 50. So we have only 2 such numbers. But when you come to this, a and b are prime numbers. So what could be possible value of a and b? So a and b possibly could be, if a is 2, b can be 3. 2 into 3 is less than 50. A is 2. This can be 5. 2 and 7. still less than 50. 2 and 11, still less than 50. 2 and 23, still less than 50. And when you go beyond this 23, 29, 2 into 29, 29 will become 58 beyond 50. So how many numbers are, how many such pairs are there? If you just count it, so 1, 3, 5, 7, 11, 13, 17, 19 and 23. So if you just count the number of ticks here, it is 8. So there are 8 such values that n can take. Values like 6, values like 10, values like 14, 2 into 11, 22, so on till 46. All these numbers will have 4 factors. So we got 2 numbers here. We got 8 more here, but we are still not done. A could be 3 and B could be next higher prime number. So could be 5. So 3 into 5 is less than 50, we can take it. 3 into 7, 21, less than 50, we can take it. 3 into 11, we can take it. 3 into 13 also, we can take it. But we can't go beyond it because beyond this is 17, 3 into 17 is 51, we can't. So we have 4 more numbers like this. Are we done? No, maybe not yet. Observe, if I take A as 5, so B can be next higher prime number because the combination of 5 with smaller prime numbers are already done. We need to go for the higher prime number. 5 with 7, next what do we get? 5 with 11, we won't take it. So that means whatever is the number of ticks that you see on the board right now should be your answer. So how many ticks do we have? 1, 2, then we have 8, 10, then we have 4, 14 and 1. There are 15 such numbers less than 50. So there are 15 natural numbers less than 50 which will have exactly 4 factors. That exactly 4 factors condition is, please note, not directly given to us. So there is something that we need to figure out ourselves by reading the conditions carefully.